Alright gang, here we go. This is for Chem 2, Unit 11. We're talking about weak acids, and we're going to talk about some Ka, do a little bit of ice tables, should be lots of fun. Alright, so weak acids. Last video we talked about strong acids. Remember, strong acids were acids that completely dissociated, right? So strong acids completely dissociate. And so really what this means is that when we calculate the pH, we can make the assumption that the concentration of the strong acid is equal to the concentration of the hydronium. All right, and that works for, those are monoprotic only. Okay, let's see, maybe we should notate that, monoprotic acid. So those are acids with just one hydrogen. All right, and so we could make that assumption. However, with weak acids are weak because they do not completely dissociate. So instead of just going to one side of the equation, they form an equilibrium. So we use the equilibrium symbol here, and you guessed it, we get to use our equilibrium skills we learned in our last unit. So we got our HA, this is just the generic weak acid equilibrium expression here, or reaction. All right, HA plus water yields H0 plus and A minus. And if we wrote the Kc expression for this, it would look something like this guy here. Okay, but we've got an A instead of a C because it's specifically we're looking at the acid dissociation constant. All right, and so really what this means is that now we can use this to get an idea of how strong our acid is. The stronger it is, the more it will dissociate, the more hydronium it will make. And so therefore, the more hydronium we have, the bigger this Ka value will be, and therefore we'll have a higher and higher Ka value. All right, and so really we can just compare the strength of an acid just by looking at the Ka of the acids. All right, instead of finding that chart that we looked at a couple videos ago, we can just look straight at that. So it's pretty handy. All right. Here's some weak acids, and you can kind of see some patterns kind of start to emerge here. So they've made the proton that ionizes the red one. So this is the hydrogen. This is your acidic hydrogen that pops up, and you can see, so of these, chlorous acid would be the biggest, the most, or the strongest acid, and then hydrofluoric is also pretty strong, but nitrous is slightly more strong than that benzoic acid. And you can kind of start to see patterns here. Things that make things more acidic are when you have like a very highly electronegative element or set of elements that are right next to the hydrogen. So a chlorous acid, there's an oxygen and then chlorine and another oxygen. All these guys are electron hogs, so they're going to really, when this hydrogen comes off, you're going to end up with a negative on this oxygen. It's really going to help balance out the rest of this charge, and it's really going to help it last as its conjugate base. All right, hydrofluoric acid, same thing. The conjugate base is this F minus. So notice that, fluorine is the granddaddy of all granddaddies for electronegativity. It really balances and keeps that negative charge stable. All right, for nitrous and benzoic acid, not only do we have that slightly that electronegative element right next to our acidic proton, but you also have some resonance that can help stabilize it. You can imagine a case where, like, if you had, this would be the conjugate base of the benzoic acid. Okay, and it would look something like this, and you could see, well, we could push this electron here and push this electron up here, and so this electron can be spread around all these other places. Okay, and so this negative charge isn't just located on one oxygen; it's actually like split between both of these oxygens because of resonance. All right, and so we kind of get the same thing here. Notice that our acetic acid has that same sort of structure. That's our carboxylic acid group. When you take organic chemistry, you'll learn a lot about that. All right, and then you can kind of see, having these negative, electronegative elements and like this resonance capability really makes life helpful. Okay, and we already talked about this at length towards the beginning of the video. Strong acids completely dissociates. Weak acids only partially dissociate. All right, now, what we want to be able to do is be able to use our ice table skills to calculate Ka from the pH. All right, so we've already learned how to calculate our K value from a concentration of equilibrium, and this works exactly the same way as what you've already mastered, except now we just have to do one additional step to start. All right, so here's our equilibrium expression for this reaction. And it says the pH of a 0.1 molar solution of formic acid at 25 degrees is 2.38. Calculate Ka for the formic acid at this temperature. All right, so we've got Ka, here's our H3+, here's our formate anion and our formic acid. All right, and so this value here, this 0.1 molar, this is our initial concentration. All right, this is our initial concentration of the formic acid. Initial concentration of formic acid. All right, and then it says here's the pH. Well, we know that the pH of anything is equal to the negative log of the concentration of the hydronium. All right, so in order to find, and remember we can rearrange this formula so that the concentration of hydronium is equal to 10 to the negative pH. So in this case, it would be 2.38. So we can find the equilibrium concentration of our hydronium to plug in here, and we can set up our nice little table. So here's our pH concentration. Right here, here's their negative 2.38. And we know these two are going to be equal to each other because they form at the same rate, right? We've got formic acid is in equilibrium with, and I'm not going to write the water because there's not really any point. HCOO minus, right? And so these form, it's a one-to-one relationship, so they're equal to each other, right? So now they've taken this value here and they've plugged it into an ice table. So here's our formic acid here, all right? Here's our hydronium and here's our formate ion, all right? And notice here's our initial concentrations. There's that 0.1 we talked about earlier, and we're starting with 0 hydronium, 0 formate. And then here is the concentration we calculated in the previous slide from the pH. This 4.2 times 10 to the minus third. All right, and we know that these two are equal to each other. All right, so that means the change had to have been plus 4.2 times 10 to the minus third, and so therefore our change, because these are both products and this is a reactant, that means this would have had to go down by that same amount. So the equilibrium concentration of formic acid was equal to this, but with sig figs it's equal to this. All right, now in this case, because we just don't have enough sig figs and formic acid is such a weak acid, we don't really have to worry. Or it turns out that the equilibrium concentration of formic acid is equal to the initial concentration, but usually you're not so lucky. All right, and then in order to calculate Ka, we simply take that value, plug it into our K value, and Bob's your uncle. Finito. All right, let's give one a shot here. Okay, oop, yeah, we don't need that. All right, niacin, one of the B vitamins, has the molecular structure shown at right. Oh, there it is. 0.02 molar solution of niacin has a pH of 3.26. What is the acid dissociation constant? All right, so let's see if we can do this. So just generally, let's write out a formula. We don't, like niacin, I mean, look at this thing. We don't really need to write all that out. Right, so we'll just call it H and I. So there's our acidic niacin, and then we're going to mix that with water. Okay, and that's going to be at equilibrium with H3O plus and Ni minus. All right, so now we got our ice table, ICE. All right, our initial concentration of niacin was the 0.020, so we'll put that there. Our water is pure substance, so it doesn't affect our equilibrium, so we can ignore that. Our hydronium and our niacinate anion are 0. All right. And so now we got to figure out an equilibrium concentration of H3O plus. Well, we know the hydronium concentration would be equal to 10 to the negative pH, so 3.26. All right, so now we go 10 to the negative 3.26, and I got 5.495. All right, now remember this guy has 2 sig figs because it's a pH, but I'm not going to round early because this isn't my final answer. 495. All right, so we're going to, that's probably good, times 10 to the minus 4th. All right, so 5.495 times 10 to the minus 4th. So that means this guy also got to that value here. 495 times 10 to the minus 4th. All right, so that means these guys both went up by that amount. And this guy would have had to go up by that amount as well. All right, which means this one would have had to go down by that same amount. So we'll subtract 5.495 times 10 to the minus 4th from that guy. All right, so the equilibrium concentration would be our 0.02 minus that value there. And I got 0.0194. All right, so that means our Ka value for this guy here, well, that's equal to a concentration of hydronium times the concentration of the conjugate base divided by the concentration of HNI, that niacin. All right. So the concentration of hydronium in equilibrium was 5.495, and we can just square this because we know these are both the same. Now that it's not always going to be so nice and neat, but you know, in the last couple of problems we've kind of been lucky, so we can take 5.495 times 10 to the minus 4th squared, and we'll divide that by our equilibrium concentration, 1945. All right. So now it's just a matter of plugging this all in. Squared divided by 0.02 minus, and I got 1.5 times 10 to the minus 5th, and I did 2 sig figs because this guy up here, well, both of this has 2 sig figs there, and this has 2 sig figs. And so that's that. All right, last little bit here for this video, calculating percent ionization. All right, this is pretty easy. This is like trying to figure out your score on an exam. Essentially what you're trying to do is figure out what percentage of the original concentration actually ionized, how much of it actually formed the ions and dissociated. All right, so all you have to do for this is you have to take your hydronium concentration at equilibrium divided by your initial acid concentration, your weak acid concentration, multiplied by 100. And this makes sense because if you had a strong acid, that means these two values would be equal to each other because all of your initial acid would turn into hydronium, and so then your percent ionization would be 100. All right, and so here they calculate it for this. This is our equilibrium. So this is the formic acid that we looked at before we did the practice problem. All right, and so this is your hydronium concentration. Here's your initial formic acid concentration, and so 4.2% of it actually ionized. And so that's pretty much it for this little bit here. Next video we'll talk about being able to use our Ka to predict our pH at equilibrium, which is by far a more useful thing to be able to do because pretty much almost every acid it has some sort of tabulated Ka value. Some chemists, spent long hours in the lab figuring out what that Ka value was for us. All right, so this isn't too bad, just more ice table practice. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.